As Daryl touched on all those concepts, we think that it was useful to map them to an example. And as the solution is quite complex, diving into example would help you to clearly understand those concepts in actions. So let's take an example and we'll smoothly dive into the demo topology that we'll propose for tomorrow. So the solution objective, as you know, is really to have multi-site VXLAN solution. So here you have site 1 at the bottom, site 2 top left, and site 3 top right, with MAN, MetroLAN, or WAN in the middle. So what we have fabric that are inside all those sites. But what about those VXLAN tunnels? You have those VXLAN overlay tunnels between sites. This is our objective. And probably that would be the most easy deployment that you will have to go. But some other solutions might be that if you've got larger sites or larger campus in site 1 here, that features multiple fabric. So let's say here you've got fabric 1, AS1, or pod 1 if you wish, and fabric 2 on the left. So here you've got 2 fabric in site 1, 1 fabric 3 in site 2, and a 4 fabric 4 in site 3. So this is the proposal of the example, so that it combines the multiple sites plus combining the fact that you have a large site with multiple pods or multiple fabrics, so 2 here. And obviously, you want to have all your VXLAN tunnels, overlay tunnels between all the fabrics. So potentially here, all the one single VLAN can be extended on all the fabrics with those associated tunnels to have the traffic going from one fabric to another fabric. Let's dive a little bit more into what it means in terms of equipment and topology. So in Fabric 1, I've got VTEP 1, which would be a border, which is a VSX cluster. We have another top of rack VSX pair, which is VTEP 2 as a logical VTEP. Then you have spine 1 and spine 2. So that is Fabric 1. Fabric 2, this is exactly the same. Instead that here I've got border VTEP 5 here, border 2, VTEP 5. VTEP 4 is a standalone. That would be a 6300. And here you see a VSF which is VTEP 3. And then you have a spine 3 and a spine 4. Again, separate fabric, but inside the same site 1 than the Fabric 1. Then you have Fabric 3, which is just a standalone. It's VTEP 6. And you have Site 3, which consists in Fabric 4. And you have a VTEP 7, which is a VSX of 8360. And here you have a VSF. So you will get some server connected. And just to make something very, I would say, close to real deployment, not necessarily you will get direct connectivity between borders. So for instance, you may have intermediate node, layer 3 node to interconnect your sites. So typically here you may say, well, I've got some spine on Fabric 2 that have a lot of ports available, maybe some port where I can support large optic, long range optic, so stuff like that, so that I will interconnect site 3 and site 2 to site 1 through spine 3 and spine 4, which are regular intermediate nodes just for underlay. And then Fabric 1, as you can see, is connected to those intermediate nodes as well. So there is no direct connectivity, for instance, I'm talking about circuit route only port between Fabric 4 and Fabric 1. However, we'll construct those tunnels between Fabric 4 and Fabric 1 and Fabric 1 to Fabric 3. So let's represent those underlay circuits with just one cloud here. And then we'll dive into the data plane, the VXLAN data planes. So one is the intra-fabric VTEP full mesh, okay, which is local to the fabric. And then we'll have the inter-fabric VXLAN between borders, and that would be full mesh as well. So let's see that in action. So in orange here, these are the intra-fabric VXLAN overlay tunnels that you see between, for instance, VTEP 1 and VTEP 2, which are those VSX. Here, it's an easy path. And then on the Fabric 2, you have those VXLAN tunnels as well, those orange tunnels. These are the intra-fabric, same on Fabric 4. Next, we have those inter-fabric VXLAN overlay tunnels that are between borders, and we want to have full mesh of VXLAN tunnels between border VTEPs. So here, typically, you'll see a tunnel between the VTEP 6 here, which is border of Fabric 3, to the border of Fabric 1, and so on. So we have this border that are identified here, and the full mesh for the blue tunnel. So then, what we really want to avoid, and that was the limit of scale that we have before, is we want to avoid having a VXLAN tunnel that is in 10.09 unnecessary, is to have, for instance, VTEP 6 here constructing a VXLAN tunnel to VTEP 3. That VTEP 3 here is a regular leaf of the Fabric 2. Let's say a top of rack in Fabric 2. And we don't necessarily want to have that VXLAN tunnel because we'll again hit a limit of a single fabric. So that tunnel is now unnecessary and not required in 10.09. So that's the difference. So in terms of, let's pick up a particular traffic between that server, that host connected to VTEP 3 on Fabric 2, site 1 to site 3 with another host connected to that VTEP 8. You'll see that we are going to use maximum 3 VXLAN tunnels consecutively. So it means that we are using an orange VXLAN tunnel, then a blue VXLAN tunnel between border, and then from the border to the leaf, another orange. Okay, so we have only one fabric, one inter-fabric blue tunnel used between any fabric to any fabric. So that's important to understand, and we'll dive into some examples where, when it's not working properly, we can have a multiple of those tunnels. Just to map to the understanding of the overlay to the underlay, you see that between this host to this host, I'm using a first intra-fabric VXLAN tunnel, then the inter-fabric that is crossing the underlay that is, in my scenario, organized this way through the spine of Fabric 2, and then from those spines of Fabric 2 back to the border of Fabric 1, and then, so that's the end of the blue VXLAN tunnel, and then we get the another intra-fabric VXLAN tunnel inside Fabric 1. So I hope this is clear in terms of topology for you to understand. Now we need to talk, so that was the data plane. Now we need to explain a bit the control plane. So what it means in terms of leaf, spine, BGP session, internal BGP session, so that's the regular session, what it means in terms of border leaf and so on. So let's get into that. So traditionally, we've got a model, simple model where we've got OSPF as the IGP or inside the fabric, and then we have internal BGP inside the EVPN address family between the leaf and the spine, which typically host as well the route reflector function for IBGP inside the EVPN address family. So those orange BGP sessions are not new. These are the existing sessions that we used to have for traditional single fabric. We add now an external BGP session inside EVPN address family between fabric. So typically, I take an example between the border of Fabric 4 and the border of Fabric 1. And you will see, I will explain a bit later what means border leader, the concept of border leader. So here, between that border and that border, I've got one eBGP EVPN session. But remember, VSX, these are two control plane. Each node in the VSX cluster, the primary and the secondary, runs their own process for BGP, for OSPF, and so on, with their own router ID. So we have not only one BGP session between the primary of that border and the primary of this border, but we have as well a BGP session from this primary of Fabric 1 to the secondary of Fabric 4. And I put here eBGP multi-hop because you understood that it was not directly connected circuits between them. It was through an underlay that is with multi-hop. So that's why this session is eBGP multi-hop. So that's an important point to retain as well. And we'll do the session between loopback. So as you understand, there is from one node two eBGP sessions. Well, obviously for the secondary as well. So that's a total of 4 sessions that you have to plan in the deployment between border leaders. So why border leaders? The border leader are the pair site, an identified pair of VSX that is responsible to do the control plane and the eBGP VPN session to the other sites for the site. So typically here, border VTEP 5 here will not have any eBGP sessions to the other side. So let's dive into more. So between Fabric 4 and Fabric 3, which are different sites, you see that I've got also those eBGP VPN sessions multi-hop between the primary to the other site and between the secondary to the other site. We have as well the same from the site 2 to site 1 of the border 1 here, VTEP 1. So these are the eBGP EVPN sessions between border leaders. And then within a site which has multiple pods, we have between the border and the border leader an eBGP EVPN session as well. So that one is local to the site. However, it's different autonomous system, AS1 and AS2. So this is still an external eBGP session, but between the border leader of the site, which is the leader in terms of inter-site connectivity to the other sites. So this notion of border leader, that concept is something that we introduce in order to simplify the configuration of the routing between the sites so that we don't have to have a full mesh between borders. So this is very important to simplify the deployment. So typically here, the session between the border VTEP 5 and the border leader of the other site, we don't want that. We don't want that to simplify again the configuration. So as well, there is no need as a simplification to have intra VSX BGP EVPN session because you have those sessions that are eBGP multi-hop. So they will never fail. They will just use the underlay routing to have that. So it means that there will be consistency between what the primary learns through the other sites and what the secondary learn as well, without the need to have the primary sending routes to the secondary as well. So it's unlike the regular IPv4 address family, typically where you have a continuity of BGP as well. Here, there is no need, thanks to the multi-hop capability that we have. So we have those external BGP multi-hop sessions for the control plane between the border leaders. So those are established between loopback. So now how we learn about those loopbacks. This is, remember, inside the fabric, we were using OSPF to learn about all the loopback addresses. So that this is fine inside the fabric, but outside the fabric, we need to learn as well those borders. So for that, we need to have an underlay control plane mechanism as well. So this is typically an IPv4 address family for external BGP to learn those loopback. And why not leveraging actually what we have already in place for inside the pod, inside the fabric? Let's use OSPF and inject OSPF into BGP and then learn the on another site the route through the injected OSPF routes inside BGP so that the routes are received on the other sides through BGP. So this is typically the role of those eBGP IPv4 unicast session that we have here, where we exchange the routing information for the loopback. So that is true for the loopback 1, that is the unicast loopback for VSX pair, or the loopback 0 for the VSF or the standalone. So Then you could think about in the deployment, shall I also do some internal BGP session for this underlay IPv4 address family? Well, on that, there is no perfect solution. It completely depends about the resiliency that you have, the topology, and so on. So typically here, I didn't put any session here, but it might be something important for reliability of some circuits. For instance, if there is one circuit failing or one switch failing, maybe you want to rely on the continuity of that BGP information in order to reach the loopback. So this is dependent on the topology, I would say. Now let's talk about the manipulation that we will process on the next hop. This is an important aspect of the solution where we have multiple pods, which is the case in this solution. First of all, let's see here between VTEP 6. So we have let's say traffic initiated from VTEP from host connected to VTEP 6 that needs to reach host behind VTEP 1. So VTEP 6 receive the autonomous system 1 here, the routes from Fabric 1, receive those EVPN routes with a next hop that is VTEP 1 here. And it does not receive that with VTEP 2 next hop. So imagine that the host is connected behind VTEP 2, does not receive the route with the next hop being VTEP 2, because the next hop must be the border so that the VXLAN, the traffic is sent to the VXLAN tunnel, the blue tunnel that ends to VTEP 1. So this is what we want as an objective. Similarly, VTEP 6 sending traffic to VTEP 5 should have all the routes from Fabric 2 learn with the VTEP 5 as a next hop and not VTEP 1. Remember, the eBGP multi-hop session that we have here is between VTEP 6 and VTEP 1. So naturally, through the mechanism of the nominal mechanism of external BGP, the routes learned on Fabric 3 would be with the next hop being VTEP 1. So we need a kind of rewriting the next hop in order to make sure that it does not happen and that we have the tunnel from VTEP 6 to the Fabric 2 that will end up to the right border, which is VTEP 5, and not to VTEP 1. If I want to have, let's say, traffic, the return traffic from VTEP 5 to VTEP 6, similarly, I want VTEP 5 to see the routes of the Fabric 3 behind the next hop being VTEP 6 and not behind next hop being VTEP 1. Remember, we have this external BGP session as well between the border and border leader, so that if I do no processing of the next hop, I will have the next hop being VTEP 1 instead of VTEP 6. Similarly, here between VTEP 1 and VTEP 5, the return traffic, it's so here what we want to make sure is that VTEP 1 receive the routes from VTEP 5 and not from VTEP 3 or VTEP 4. So there is a kind of process to be set in different positioning of the BGP mechanism so that you will understand that. So there is 3 things to get into that. So I'm going to explain that. So the next hop is advertised from the border and from the border leader is going to be explained here. So let's get into that. So I've got some servers connected. I've got VRF1, VRF2, VRF3 and 4 are for examples. I've got here some in green, this is VRF1, in orange, this is VRF2, and you see there is multiple subnets per VRF1 here. Okay, and different subnets as well for VRF2. that we are going to use. So now I want to analyze what are the next hop received here. So on VTEP 6, I want to check, for instance, for the VRF2 here, which is in orange, the routes that are received for 10.2.21.0. So that 10.2.21.0/24 is the subnet that is located on VTEP3 here. So that's information that an LRI is received here, and you'll see that the next hop for that is VTEP5. So this is our objective, just to make it clear on that drawing. So now, how we are going to do that, knowing that we have the capability to have the new capability that we introduced for internal BGP inside the address family, which is next hop self. That we have as well the nominal behavior of BGP for external BGP peering, which is to replace the next hop with the next hop of the peer. So that is, for instance, when VTEP1 receives any routes from VTEP5, the next hop for that route will be replaced by VTEP5. You have nothing to do. That's the traditional BGP way of handling next hop rewrite for external BGP. However, for internal BGP, any route that is learned from VTEP5 that is to be populated to the route reflector, for instance, will be maintained with the next hop being the remote fabric. So we want to change that. So that's why we introduce a new command, which is next hop self for the internal BGP session. So what we do here, AS2 routes send from the fabric 2 to fabric 1, okay? On that one, we just make sure that fabric 1 will receive that with the next hop being reset thanks to the nominal behavior of external BGP. So there is nothing to do here. And you'll see that there is another mechanism that is used, which is the rewrite of the router MAC for L3 VNI. I will come into that. So next is that the VTEP1, the border leader, sending those routes to the other fabric, let's say fabric 3, for instance. That guy should not change the next hop. So this is something not natural, not in nominal behavior of external BGP to maintain the next hop. So what we want is to maintain the next hop for AS2 and AS4. So any routes learned through that eBGP session from Fabric 4 and to Fabric 1 will be forwarded as well to Fabric 3. So for AS2 and AS4, we do not want to touch the next hop. We want to maintain the next hop as the original next hop, so that when, for instance, VTEP 6 here receive the routes, it will construct and send those packets for destination being Fabric 4 to VTEP 7 instead of forwarding that to VTEP 1. So I think I repeat that many times, so I think it's clear now. That the same for AS3, sending the routes. Okay, so here this is the natural next hop self for external BGP, so that's why I call that E next hop self. Then similarly, we want Fabric 2 to receive the routes of AS3 and 4 with next hop unchanged, and sending AS1 with E next hop self as the regular mechanism. And then you have all the similar output, or I would say inbound, outbound route advertisement explained in that drawing, what we want to do between fabric.